Hi everyone. In this video, we'll be evaluating the integral from 0 to infinity of log x over 1 plus x squared dx using complex analysis and contour integration. The first step is to define a complex function f of z equals log squared of z divided by 1 plus z squared. We raised the logarithm so that we can recover the integral in the future. You'll see this. So f of z has a pole at z equals -1, a branch point at z equals 0 because of the logarithm, and a branch cut from 0 to positive infinity. With this in mind, we can construct a contour. So what we'll do is we'll have a path called psi2 go under the real line, and then a small detour, gamma, that goes around the branch point, and then we'll return with a path called psi1. To close the contour, let's close it with a path called big gamma, and let's name the entire thing C and make it go counterclockwise. By Cauchy's residue theorem, the contour integral over C is equal to the integral over psi1 plus the integral over psi2 plus the integral over little gamma plus the integral over big gamma equals 2 pi I times the residue at z equals -1 of our function. Now, I'll explain this at the end of the video, but as the radius of little gamma goes to 0 and the radius of big gamma goes to infinity, the integrals over little gamma and gamma go to 0. Now, let's focus our calculations on psi1 and psi2. We know that the argument of z is in between 0 and 2 pi. And recall the definition of the complex logarithm. Squaring it on both sides, we see that log squared of z equals log of the absolute value of z plus I times the argument of z squared. We can write down the path integrals over psi1 and psi2. Keep in mind that the integral over psi2 has an argument of 2 pi. We can switch the bounds of integration and add a negative for psi2. And then we can also simplify the numerator. Now, the sum of psi1 and psi2 will be as follows. We can combine it under one integral sign, and we'll see that a lot of things cancel out. We can distribute the integral, and let's evaluate the integral on the right hand side. This is equal to 4 pi squared times 1 over 1 plus t evaluated at the bound 0 to infinity, which is simply just 4 pi squared. Now for the integral on the left hand side, notice that it's actually just 4 pi I times big I, our target integral. Notice how we recovered our target integral with the log squared trick. Plugging this value back in, we can see that the contour integral over C is equal to minus 4 pi I times our target integral plus 4 pi squared. Now, the only thing left to do is to calculate the residue. The residue, it's a second order pole at -1, so it's equal to 2 pi I times the limit as z approaches -1 of the derivative of z plus 1 squared times log squared of z over 1 plus z squared. The 1 plus z squares cancel out, and the derivative of log squared z is 2 log z over z. We can plug in z equals -1, and note that the log of -1 is equal to I pi. So we're left with 2 pi I times -2 times I times pi, which is simply 4 pi squared. Now we have a pretty simple equation to solve. We can subtract 4 pi squared on both sides and divide by -4 pi I. Now we can conclude that our target integral I is equal to 0. For those of you who stayed, let's present an argument now for why the integrals over gamma and big gamma disappear. Recall our complex function f of z equals log squared z over 1 plus z squared. As we increase the radius for big gamma, 1 plus z squared, the denominator, will grow faster than log squared of z. This means that the integral over big gamma will disappear. But what about little gamma? Well, we can write the integral of little gamma as the integral of all complex numbers an epsilon distance away from the origin of f of z dz. We can take the absolute value on both sides as well. Now let's parameterize gamma. Z equals epsilon e to the I theta, and dz equals I epsilon e to the I theta d theta for theta in range 0 to 2 pi. Then we can use the triangle inequality to take the absolute value of everything on the inside. Note that the absolute value of I epsilon e to the I theta is simply theta. Also, we can use the reverse triangle inequality on the denominator. Note that, again, the absolute value of epsilon e to the I theta is simply epsilon. We can also use the complex definition of the logarithm to expand out the numerator. And we can expand the square. We can pull epsilon over 1 minus epsilon squared out and write the integral as follows. We can distribute the integral, and we're left with the following: that the absolute value of gamma is less than or equal to epsilon over 1 minus epsilon squared of a whole chunk of math. Now, the integrals over with respect to theta are just constants, a, b, and c. So, as we take the limit as epsilon approaches 0, we get that it's equal to epsilon times log squared of epsilon a plus 2 epsilon log epsilon b plus epsilon c. Now, because the limit as epsilon approaches 0 of all these terms is also 0, the entire limit is 0. Since the absolute value over gamma is less than or equal to 0, we conclude that the integral over gamma must tend to 0. Now, in this final step, if we let epsilon, or the radius, tend to infinity, we would also show that the integral over gamma also tends to 0. That's the end of the video. I hope you enjoyed.